all. Let us continue our learning of the subject Big Data Analytics. The target audience is Semester 7 CSE students. Today's topic under discussion will be from Unit 2. Unit 2 we had started discussing HDFS architecture, and today we'll discuss anatomy of file read, anatomy of file write in HDFS, parallel copying by distcp. These are the three topics from Unit 2 of the subject Big Data Analytics. For today's topic discussion, we will be using the prescribed textbook by Tom White, Hadoop, the Definitive Guide, 3rd edition orally. So this is the book from which today's contents are derived totally. So let us start our discussion. So let us look at the first diagram under the heading anatomy of a file read. So this is telling the flow of HDFS client reading a file. So as you can see here, there is a client on the client node, the HDFS client. There is a name node and there are data nodes. The HDFS client, as you can see, issues an open to the distributed file system, that is HDFS distributed file system. The name node will be telling the address of the data nodes. The HDFS client will be issuing a read, and through FS data input stream, the data will be read and ultimately a close will be issued by the client. But let us see in detail how this flow will be occurring, or how the sequence of events when reading a file under HDFS happens. So as mentioned here, the HDFS client issues an open on the file system object. So actually this is an instance of distributed file system. So HDFS client is issuing an open. The distributed file system is issuing a remote procedure call to call the name node, So the name node will be determining and telling the location of the first few blocks. The name node will be returning the address of the data nodes which have the copy of that block to be read. The data nodes are sorted according to their proximity to the client. What the distributed file system will be doing, it will be returning an FS data input stream. Why? Because it supports file seek to the client for it to read data from. The FS data input stream wraps a DFS input stream which manages both the data node and the name node IO. The distributed file system returns an FS data input stream. The client then will be calling the read on the stream. The DF input stream, which has stored the data node addresses, connects to the first closest data node for the first block in the file. Data is streamed from the data node back to the client, which calls read repeatedly. So read is issued repeatedly by the client, that you have to remember. So ultimately when the end is reached, the DFS input stream will close the connection and it will be finding the next block for next data node for the next blocks. And this is transparent to the client. The blocks are read in order. The DFS input stream will call the name node to retrieve the data node locations for the next batch of blocks to as needed. When the client finishes reading, it calls a close on the FS input data stream. This is the step 6, you can see. Close is issued. Now, while reading, if there is an error communicating with the data node, the DFS input stream will try the next closest one for the block. The DFS input stream will also remember the data nodes that have failed. The DFS input stream verifies checksum. If there is a corrupt block, the DFS input stream attempts to read a replica. It reports the corrupted block to the name node. So, very interesting thing is of this design is the client is contacting directly to the data node for data retrieval, and name node is kind of a guide so that the best data node for each block is found. So this lets HDFS scale to a large number of concurrent clients. What is the job of the name node then? It is servicing the block location request. And what it does not do, it serves data. So otherwise it becomes a bottleneck as the number of clients do. So this is in crux about how a file read is happening sequentially in a HDFS ecosystem. Let us go for file write now. So let us look at this diagram for writing the file in the HDFS ecosystem. So client is issuing a create. The distributed system file system is issuing a remote procedure call to the name node. So this create without the blocks happens. The name node will be identifying the data nodes where the data can be written. The client will be issuing a write through FS output data stream, just as there is FS data input stream in the read. The write packets are sent to the data node, and you can see there is a pipeline of data nodes here. So the first data node, from there the data goes. So ultimately close is issued. Let us look at this in detail. So first step is a create, because you need to create a new file. So the client is issuing a create on distributed file system. The distributed file system is issuing a RPC call, remote procedure call to the name node, telling it what? It wants to create a new file. Okay. So there are no blocks associated with it presently. What the name node does is it will be checking if the file already exists, whether the client has permission to create the files. Then the name node makes record of this new file. Like read, the FS data output stream wraps a DFS output stream, which will be handling the communication between data node and the name node. The client writes the data. The DFS output stream splits them into packets and writes to an internal queue called as a data queue. The data queue is consumed by the data streamer. So what the data streamer does, it asks the name node to allocate new blocks by picking a list of suitable data nodes to store the replicas. These data nodes form a pipeline. The replication factor by default is 3. So there are 3 nodes in the pipeline. There are 3 nodes, 1, 2, 3. The data streamer streams the package to the first data node, which stores each packet and forwards it to the second data node in the pipeline. The second data node again forward to the third data node. The DFS output stream maintains one more internal queue for acknowledgements called as acknowledgement queue. A packet is removed only when it has been acknowledged. If a data node fails in writing the data, what will happen? The pipeline is closed. The packet in the acknowledgement queue, if they are added, they are kept in front of the data queue. Uh, the blocks are given a new identity which is stored to the name node. The failed data node will be deleted. If at all it recovers again, it will be removed from the pipeline. A new pipeline is created for the good data nodes. The rest will happen as per normal flow. Post whatever under replicated data was there, those arranged. You have dfs.namenode.replica.min, which by default is 1. As long as it is maintained, the write will be succeeded and the blocks will be asynchronously replicated across the cluster until the target factor is, what is the default replication factor? 3. So once the data writing has finished, the client calls a close. This action flushes all the remaining packets to data node pipeline and waits for acknowledgement. Post that, it will be contacting the name node to signal that the file is complete. The name node knows which block the file is made up of. It has to wait for blocks to be minimally replicated before returning successfully. How replication happens? Replication, by default, the replication factor is 3. It means 3 copies will be created. Now there is a trade-off. What is the trade-off? The trade-off between bandwidth and the trade-off between how do I put it, locality. And so what usually the Hadoop does is, it will be keeping the first replica in one rack, the second replica and the third replica on the same rack, but on different nodes. This is what is the replica pipeline usually happens. Let us come to the last point of today's discussion, that is parallel copying. Okay. For parallel copying, we'll be using a program called as distcp. We as in Hadoop users. Okay. So suppose you are using this command, Hadoop distcp file1 to file2. What is happening? You are copying one file to another file. You can also copy directories using this command, Hadoop distcp dir1 to dir2. Let us say dir2 does not exist, it will be created. If dir2 is already there, then the dir1 will be copied underneath with this path dir2/dir1. If you don't want it, you can use the overwrite option. You can also update only those files that have changed using the update option. Say for example, Hadoop distcp update dir1 dir2. Distcp program is implemented as a map reduce job. The copying is done by the maps which are running in parallel across the cluster. There is no reducer. Each file is copied by a single map. Distcp gives the same amount of data to each map. So the default value for map is 20, but that can be changed using the m argument to distcp. What usually we found out is distcp is used for transferring data between two HDFS clusters. Suppose you want to create a backup of the first cluster, you can use this kind of command, distcp update delete p HDFS the first and HDFS the second. Here why this delete flag is used? It will be deleting any files or directories in the destination that are not present in the source. What is the meaning of this flag p? Status information like permission, block size, replication. Suppose you have incompatible versions of HDFS, then you can use web HDFS protocol. Say for example, Hadoop distcp web HDFS like this. Now, whenever we are copying, we should ensure that cluster balance is maintained. So if cluster balance is maintained, Hadoop works best. Okay. Say for example, when you are using distcp, uh, you may disrupt this. For example, you give an option called as M1. Only single map will be used, which makes the system slow, and cluster resources are not used efficiently. It means what? The replicas are retained on the same node. That's why you use this CPU with default 20 maps per node. So thank you for listening this. Let us continue our learning of big data analytics.